In this nutshell, you can practice your USART programming skills. You will write the code for a transmitter and receiver for a car door lock. In this case, you will base it on a state diagram. And if you do find this video useful, please like and subscribe. We are going to repeat the code that we did previously, but we are going to use a state diagram rather than a structure diagram. And the code is for a remote key lock for a car. It's broken into two parts, a transmitter and a receiver. So for the transmitter, we are connecting to the car via Bluetooth. We send a 9-bit code. Bit 8 shows whether the command is to lock, which is 1, or unlock, 0, the car. And then we have a key code 8 bits from bit 7 to 0. While the lock or unlock button is held down, you will continuously transmit the 9-bit code and flash a LED every 10 milliseconds to indicate the key is actively transmitting. So pause the video now and write the pseudo code and the state diagram for this problem. We can see the pseudocode and the state diagram for this problem. We have three states: idle, transmit unlock, and transmit lock commands. So in the idle state, if the unlock button is pushed, we transmit the unlock command and go back to the idle, and that will repeat while the unlock button is pushed. If the lock button is pushed, we will go to the transmit lock command and then return back to the idle state, and that will repeat while the lock button is pushed. And we're setting up the GPIO and USART even parity, 9 data bits, 1 stop bit, and 4800 baud. So now pause the video and try to write the code from the state diagram. Looking at the C code, we have our defined statements, and we are looking at our state variables or constants here. If we scroll down to our main code, we have the transmit key code, we have a state variable, and we have a while one and the switch. And the switch is used to go between our different states. So we're looking at the state variable here. If the state variable was in idle, then if the lock button is pushed, we go to the state transmit lock command. If the unlock button is pushed, we go to the state transmit unlock. In the state transmit lock, we wait for the buffer to be empty. We first set bit 8 in TXB82 to a 1. Then we transmit the key code, and that will send the 9 data bits. Then we turn the LED on and off to indicate we're transmitting. If the state was unlocked, then we go into the state unlock. We do the same thing, except we clear that bit 8, and send the data. So looking at the registers, the first register is the UCSRnA register, shown here, and we are looking at bit 5, that's the UDRe is empty flag. So that will go to a 1 when that data register is empty. So looking at the setup for the USART2, we are transmitting at 4800 baud. We've got a clock frequency of 8 meg, so 103 is loaded into the UBBRnH register. Now we are only transmitting, so we are looking at bit 3 here for this UCSR2B. Bit 3 is set to a 1 to turn on the transmitter, and then these bits here, bit 2 and bit 2 and 1 in UCSRnC, are used for the frame size. We'll look at the table in a second, but that should be set to A1. So looking at the UCSR2C register, bits 7 and 6 are used to make the mode asynchronous, so they are set to 0, 0. We are doing odd parity, so we are looking at these bits here, 1, 1. They are bits 5 and 4, so 5 and 4 are 1, 1. We're doing 2 stop bits, so therefore the UCSR, this bit here, bit 3 should be set to a 1, and then finally we are doing 9 frames, or 9 bits in the frame, so these bits here, UCZN1 and Z0 should be set to a 1 as well. That's shown there. The transmitter is being fed out port H1, so we set that for an output. The LED is on port C7, so we set that for an output, and we start with the LED off. So the second part of this problem is the receiver on the car, which is used to lock and unlock the car. We have 3 outputs, the indicators, a beeper, and the lock. The serial format is the same as the transmitter. I won't go through this, I'll let you read it and see if you can form that into some coherent state diagram. This will take you a few steps to go through and try and word this in some pseudocode and the state diagram. Note, you should test the parity bit, and to prevent double triggering, you must wait until the key transmitter finishes its current transmission before you respond to a new command. So pause the video and write the pseudocode and the state diagram for this problem. I have written the pseudocode and state diagram here. Now once again, this does take a bit of time to try and work out the best plan. So before you write any code, you should clearly have your state diagram written and your pseudocode. From there you can just straight away write your code without having to think. The thinking occurs here. So basically we have an idle state. We're a receiver. If we receive new data, we check the parity. If there's an error, we go back to idle. If the parity is good, then we check the key code. If the key code is wrong, we go back to idle. If the key code is good and the command was to unlock the car, we unlock the car and go to our debounce. If the key code was lock the car, then we lock the car and go to our debounce. The debounce waits for the transmission to be finished, and then we go back to idle. So it does take a while to get to this point, but when you get there, your code is clear and precise. So pause the video now and see if you can write the C code from the state diagram. Looking at the C code for the receiver, we start off with the delay.h. We're including the library, and that means we need to define the clock frequency running the CPU. We are looking at receive buffer full, which is bit 7 here, and so that's looking at bit 7, and we're looking at the parity error bit, which is bit 2, so that's looking at the 2 flags. The indicator's on port B, bit 6, the lock is on port C, bit 0. We also are looking at the output of the port, so that we know if the car is locked. The beeper is on port D, bit 5, and then we have state constants, state idle through to state debounce. Looking at the main code, we set receive key code to the receive key code value. we use a while one, and then we use a switch statement that we use for our state machine. So if we look at the cases here, they corresponding to the states shown here. If we're in the idle state, if we receive new data, then we go to the state check parity. In that state, if there's a parity error, we clear the parity flag, and then we go back to the idle state, else we go to state check key code. And here, the first thing we must do is we must look at bit 8 before we read the lower 8 bits. So if it's a 1, we set a flag lock car, else we clear lock car flag. We load the key code itself into our received data, and if it's correct, then we move to the state lock car or state unlock car. If the key code was incorrect, then we go back to the idle state. So looking at the lock car, if the car is locked, then we just flash the indicators, else we lock the car and flash the beeper and indicator 6 times. Then we go to the state debounce. We do a similar thing for the unlock state here as well. Finally, in the debounce, what we're waiting for is we're waiting for the transmitter to stop sending data. So we check the receive buffer full, which means it's sending data. We clear the receive flag, and we have a debounce timeout set to 50. Now if we don't receive data, then we decrement the timeout until the timeout goes to 0, and then we go back to the state idle. So that is our debounce part of the code. Looking at how we set up the USART2, first thing we do is we set the baud rate. We want 4800 baud. We use the tables from the datasheet. We have an ATmega clock, so therefore 103 is a value that's loaded into the baud rate register in the lower byte. Then we're setting up the UCSRnA. The first bit here is shown down here. This is bit 4 that powers on the receiver. And finally, this bit here is used in conjunction with these 2 bits here in UCSR2C. Those are those 2 bits shown here. And we want 111 for 9-bit data frame. And finally, looking at the other bits in the UCSR2C register, bits 7 and 6 are the mode of operation, so we want to do asynchronous, so they are 0, 0. Bits 5 and 4, they are linked to parity. We want even parity, so they should be 1, 0. We are using 1 stop bit, so therefore bit 3 here, it should be a 0, and we've described these other 2 bits previously. The final bit is used if you're doing synchronous mode of operation, so don't worry about it. And finally, we have the indicator on port B, bit 6, the beeper on port D, bit 5, and the lockers on port C, bit 0. So we set those for output on the data direction register. And we have a small routine here to flash the LEDs a number of times. Out of interest, I have combined both the car transmitter and the car receiver in the same code, same program, and I'm using the megaPro feature where I can switch the output of the USART transmitter back into the input of the USART receiver. So I can simulate both the transmitter and receiver at the same time. So the code shown here, this is Microchip Studio. We've got our defines for the receiver and the transmitter. This is our code here for the transmitter state machine. There's the code here for the receiver state machine. We looked at all that before. The main difference is that I have a loopback switch, which is on PH2, and I turn the loop switch on. So if I download this into megaPro board, and we see that running. So once again, this here is the indicator for the lock, PC0. This is the indicator for the transmit, PC7. We have the lock button here and the unlock button here. And then we have the indicators shown by the light here, and we have the speaker for the beeper. So if I lock it, we can hear the beeper and lock going, and holding the key down, nothing's happening. I push the lock again, and the indicator came on for 1 second, showing it's already locked. If I push the unlock button, we can see the button, the indicator and buzzer pulse twice. Holding the key down does nothing. If I release the key, push it again, we get the light coming on to say that it's already locked. So we can see both the transmitter and the receiver working together.